December 1972. The air above Hanoi tastes like kerosene and fear. Inside a concrete bunker 40 miles north of the city, a Soviet radar technician leans forward, eyes locked on a screen that glows amber in the darkness. The fan-song radar pride of Soviet air defense engineering sweeps the night sky in steady, mechanical rhythm. Each rotation paints the world above in phosphorescent truth. Altitude, bearing, velocity. The Americans are coming. They always come at night. He counts them as they appear over the mountains. 8 targets. 12. 20. The shapes materialize like ghosts stepping through fog. Each one a B-52 Stratofortress, carrying enough ordnance to erase city blocks. His fingers move across the console, tracking vectors, calculating intercept solutions for the SA-2 missiles waiting in their launchers outside. The mathematics of death, rendered in glowing green coordinates. North Vietnamese officers crowd behind him, voices sharp with urgency, demanding confirmation, demanding action. He gives them numbers. Altitude, 30,000 feet. Speed, 400 knots. Range, closing. The bunker smells of cigarette smoke and electrical ozone and human sweat. The concrete walls are 3 feet thick, designed to withstand anything except a direct hit. The air conditioning struggles against the tropical heat outside, creating a climate that's neither cool nor warm, but somehow both simultaneously. The technician, his name is Viktor Petrov, though that detail will never appear in any American intelligence report, has been at this station for 8 months. He knows the rhythms of American bombing raids the way a fisherman knows the tides. They come in waves. They follow patterns. They can be predicted, tracked, engaged. Tonight feels different. The formation is larger than usual. The Americans have been escalating for weeks, sending bigger raids, hitting harder targets. Intelligence suggests they're trying to force negotiations, to break the will of Hanoi through sheer destructive weight. Petrov doesn't concern himself with politics. He concerns himself with mathematics. Angle, velocity, trajectory, the science of interception. His radar can see 100 miles in any direction. His missiles can kill at 40 miles. The Americans know this. They know he's here, watching. They come anyway. The screen shows them crossing into North Vietnamese airspace. The formation is tight, disciplined. The bombers maintain altitude and speed, not attempting evasive maneuvers yet. They're still too far out. They're relying on their jamming systems, on electronic countermeasures, on the hope that Soviet radar can be overwhelmed with enough electromagnetic noise. Sometimes it works. Usually it doesn't. Petrov has guided successful intercepts against 34 American aircraft. He has the statistics committed to memory: 34 kills, 41 launches. An efficiency rate that would have earned him commendations in Moscow, if Moscow cared about anything except aggregate numbers. He selects the lead bomber, designates it as priority target. The tracking solution builds on his screen range decreasing, altitude constant, bearing steady. The bomber is following a predictable approach vector, probably guided by radar navigation, probably committed to a specific ingress route. Predictability is death in air combat. The Americans should know this by now. His hand moves to the engagement control. Behind him, the North Vietnamese battery commander is shouting into a field telephone, coordinating with other sites, building an interlocking web of fire. The SA-2 missiles wait in their launchers, pointed at the sky, ready to transform 34 kills into 35. Petrov's training is extensive. He's operated this system in conditions ranging from clear skies to monsoon storms. He's engaged single aircraft and entire formations. He's watched missiles track, correct, detonate. He's seen American bombers come apart in mid-air, breaking into pieces that tumble toward Earth trailing fire. He feels nothing about this. It's mathematics, pure, clean, objective. The engagement solution locks. His screen shows a firing solution with 93% probability of kill. He's launched at worse odds. He toggles the commit switch, feels the solid click under his thumb. Outside, in the darkness, two missiles ignite, their rocket motors transforming fuel into thrust into ascent. They climb on pillars of white flame, visible for miles, correcting their trajectory based on guidance signals transmitted from Petrov's radar. The Americans will see them coming. They always do. It won't matter. Then the screen goes white. Not dark, white. A sudden wash of static that drowns every return signal, every echo, every carefully plotted trajectory. Petrov's hand freezes over the controls. His first thought is equipment failure. His second thought is jamming. But jamming doesn't look like this. Jamming creates noise, interference, scattered returns. This is something else. This is complete signal corruption. The screen has become meaningless, a blank canvas where there should be targets. He adjusts gain, checks connections, cycles through frequencies. Nothing. The radar is transmitting. He can verify that from the equipment readouts. Power output is normal. Antenna rotation is normal. But the returns, the echoes bouncing back from objects in the sky, have vanished. Or more accurately, they've been replaced by something that looks like signal but contains no information. It's as if someone has painted over his vision with white noise. Behind him, someone shouts in Vietnamese, someone else in Russian. The words blur together into a single question that no one can answer. Where did they go? The missiles launch anyway, climbing blind into the dark, guided only by their last known trajectory data, hoping that the bombers maintained course and speed. It's a futile hope. The Americans aren't stupid. If they've found a way to blind Soviet radar, they're not going to fly straight and level. Petrov watches his missiles climb on his backup tracking systems, watches them reach intercept altitude, watches them detonate harmlessly in empty sky. Somewhere above, American crews watch the telephone poles of flame arc up toward them, then spiral away into the darkness, chasing phantoms. The bombers press on. Petrov can hear them now, a distant rumble that penetrates even the thick concrete of the bunker. The sound of multiple Wright-R 3,350 engines, each one producing over 3,000 horsepower, multiplied by 8 per aircraft, multiplied by 20 aircraft. The mathematics of sound. He knows from the volume and direction that they're passing nearby, probably 30,000 feet up, probably still in tight formation. He can hear them, but he cannot see them. His radar, the most sophisticated air defense sensor ever deployed in combat, has been rendered useless by something he doesn't understand. The white static on his screen begins to clear, slowly, gradually, like fog burning off a morning field. The returns start to come back, but they're wrong. He sees targets where there shouldn't be targets. 3 bombers appear at 12,000 feet, altitude that makes no sense for a B-52 on a bombing run. 5 more appear 30 miles south of where the formation should be. The tracking solutions are impossible. The vectors don't match. It's as if the sky has filled with ghost aircraft, phantom bombers that exist only as electromagnetic echoes. Petrov is 34 years old. He studied radio engineering at Leningrad Polytechnic Institute. He served in the Soviet Air Defense Forces for 8 years before being posted to North Vietnam as a technical advisor. He has operated radar systems in Siberia and East Germany and Syria. He has guided missiles against real targets and simulated targets, and targets that turned out to be flocks of geese. He has seen equipment failures and operator errors, and atmospheric anomalies that created false returns. He has never seen anything like this. The North Vietnamese battery commander is screaming at him now, demanding explanations, demanding targets, demanding that he do his job and kill the Americans who are now dropping bombs on Hanoi. Petrov tries to explain that his equipment is showing impossible data, that he cannot trust what he's seeing, that the Americans have deployed some kind of electronic countermeasure that corrupts radar returns rather than simply jamming them. The commander doesn't want explanations. He wants results. More missiles launch. From other sites around the city, SA-2 seconds climb into the night, dozens of them, filling the sky with fire. Some are guided by radar. Some are fired blind, barrage fire into the known bombing corridors, hoping to get lucky. The Americans have done something unprecedented. They found a way to make radar, the technology that defined air defense for 30 years, unreliable. Worse than unreliable. Deceptive. The radar is showing him things, but he cannot trust that those things are real. In the distance, he hears the crump of bombs detonating. The Americans have reached their target. They're attacking something north of the city, a rail yard, probably, or fuel depot. The explosions create their own returns on his radar, brief flares of electromagnetic noise, then more white static, then more ghost returns that make no sense. The formation must be turning for home now, heading back toward Thailand or Laos or wherever they launch from. He tries to track them. His screen shows bombers in 3 different locations simultaneously. His tracking computer attempts to follow all of them, cannot reconcile the contradictory data, drops lock entirely. Petrov sits back in his chair and stares at his screen and feels something he hasn't felt since the Great Patriotic War, when he was a boy watching German bombers fly over Leningrad, while Soviet anti-aircraft guns fired uselessly into the sky. The cold, crawling realization that the enemy possesses something beyond his understanding, something his training never prepared him for, something impossible. The Americans are gone now. The sky is clear. His radar returns to normal function, showing exactly what it should show. Empty sky, distant weather returns, the occasional bird flock. The equipment diagnostics run green across the board. Everything is functioning perfectly, which means the problem isn't his equipment. The problem is that the Americans have found a way to lie to it, to inject false data, to make the machine see things that aren't there. He will spend the rest of the night writing his report. He will use careful, technical language to describe what he witnessed. He will speculate that the Americans have deployed a new form of electronic warfare system that generates false radar returns. The phrase will be translated, analyzed, forwarded up the chain of command. Soviet engineers will read it in Moscow and begin urgent research programs to understand what happened and how to counter it. But on this night, in this moment, Petrov simply sits in his concrete bunker and understands that the war has changed. The Americans have stopped trying to overpower Soviet radar and started trying to outsmart it. And in the long arc of military history, intelligence always beats strength. 7 years earlier, the war in Southeast Asia was different, simpler, more predictable. The Americans flew their bombing missions over North Vietnam with near impunity. Their aircraft were faster, more capable, more technologically sophisticated than anything the North Vietnamese possessed. The MiG-17 interceptors that rose to challenge them were outclassed by American fighters. The anti-aircraft artillery that peppered the sky was dangerous but survivable. The Americans lost aircraft. Of course, war always extracts its toll, but the losses were acceptable, manageable, within predicted parameters. Then the Soviet Union began deploying SA-2 missiles to North Vietnam. The SA-2 guideline was a technological marvel, a weapon that represented 2 decades of Soviet research into surface-to-air missile technology. It was 35 feet long, weighed over 5,000 pounds, and could reach speeds exceeding Mach 3. More importantly, it was guided by the fan-song radar, a sophisticated tracking system that could lock onto aircraft at ranges exceeding 30 miles and maintain that lock through most evasive maneuvers. The missile itself was relatively simple: a rocket motor, a guidance section, a warhead containing nearly 500 pounds of high explosives surrounded by steel rods designed to shred aircraft. But the guidance system was extraordinary. The fan song operated across multiple frequency bands, making it difficult to jam effectively. It could track multiple targets simultaneously. It could distinguish between real aircraft and chaff clouds. It could adjust for evasive maneuvers, predicting where a maneuvering aircraft would be rather than where it had been. Soviet engineers had designed it specifically to counter American bombers, and they had succeeded magnificently. The first American aircraft fell to an SA 2 inches, July 1965. An F-4C Phantom, flying a routine bombing mission over North Vietnam, was tracked, engaged, and destroyed by a missile that climbed out of nowhere and detonated close enough to tear the aircraft apart. The crew ejected successfully. They were captured, spent the next 7 years in prison camps, and returned home in 1973 with stories about a weapon that seemed almost prescient in its accuracy. More shoot-downs followed. In August, an F-105 Thunderchief disintegrated over Thai Nguyen. In September, 3 aircraft fell in a single week. The Americans responded with iron bombs, trying to destroy the SA-2 sites before they could launch. The North Vietnamese responded by building more sites. By 1966, there were over 100 SA-2 batteries scattered across North Vietnam, a network of interlocking coverage that made every bombing mission a gamble with death. The American solution was electronic warfare. If the fan song radar guided the missiles, then jamming the radar should render the missiles useless. The Air Force deployed EB-66 electronic warfare aircraft to fly alongside bomber formations, transmitting powerful noise signals designed to overwhelm enemy radar. They developed jamming pods that could be carried by individual aircraft, each one transmitting interference across multiple frequency bands. They trained pilots in evasive maneuvers specifically designed to break radar lock. For a while, it worked. The jamming systems degraded SA-2 effectiveness. Loss rates stabilized. The North Vietnamese shot down fewer aircraft. The Americans congratulated themselves on their technological superiority and continued bombing. Then the Soviets adapted. The fan-song radar was upgraded with better signal processing, allowing it to filter jamming noise and lock onto aircraft even through heavy interference. The SA-2 missiles received improved guidance systems that could home on jamming signals, turning the American countermeasure into a beacon. The North Vietnamese changed tactics, launching missiles in ripples, saturating the sky with threats, forcing American pilots to choose between breaking formation or maintaining course through the threat. By 1967, the electronic warfare competition had become an arms race, each side developing new capabilities designed to counter the other's latest innovation. The Americans deployed the ALQ-87 jamming pod, capable of generating powerful noise across multiple frequency bands. The Soviets responded with frequency-hopping radars that could switch operating frequencies faster than the jamming pods could follow. The Americans developed chaff dispensers that could fill the sky with radar-reflective material. The Soviets developed radars that could see through chaff clouds. It was exhausting. It was expensive. And increasingly, it wasn't working. American loss rates over North Vietnam remained unacceptably high. The B-52, the iconic symbol of American strategic air power, a bomber designed to carry nuclear weapons over the Soviet Union, was proving vulnerable to weapons specifically engineered to destroy it. The Strategic Air Command had never intended to use B-52 seconds in tactical bombing roles over heavily defended targets. The aircraft was designed for high-altitude nuclear strikes, not low-level conventional bombing through dense surface-to-air missile coverage. But Vietnam was not a nuclear war. It was a grinding, attritional conflict where strategic bombers were pressed into tactical roles, flying missions they were never designed for, facing threats their designers had never anticipated. The results were predictable. During Operation Linebacker I in 1972, B-52 loss rates averaged 3% per mission over heavily defended targets. 3% doesn't sound catastrophic until you calculate the odds of surviving a tour. A pilot flying 30 missions over North Vietnam had a 60% chance of being shot down. The Air Force needed a solution. The approved solution involved years of research, extensive testing, careful evaluation of multiple competing designs, billions of dollars in development costs. The institutional machinery of defense procurement moved slowly, methodically, ensuring that every system met specifications, that every component was tested to failure, that every possible edge case was considered. The pilots didn't have years. They had tonight's mission, tomorrow's mission, next week's mission. Every one of them a roll of dice where the house held the advantage. Captain Paul Crenshaw understood this in his bones. Crenshaw arrived at U Tapao Royal Thai Naval Airfield in March 1972, with a background that made him unusual among Air Force officers. He'd studied electrical engineering at MIT, focusing on signal processing and electromagnetic theory. He'd worked briefly at a defense contractor before joining the Air Force, where his test scores and technical background had qualified him for electronic warfare officer training. He was smart in a way that made career officers nervous, capable of seeing problems that others missed, unwilling to accept official explanations that didn't match observed reality. His first month in Thailand involved flying combat missions as an electronic warfare officer aboard B-52 seconds. His job was to operate the jamming systems, monitor threat radars, deploy countermeasures, and provide the aircraft commander with real-time assessment of enemy air defenses. It was technical work that required both deep understanding of electronic warfare principles and split-second decision-making under combat conditions. What Crenshaw noticed, what troubled him, was that the jamming systems didn't work as advertised. The ALQ-87 pods were supposed to blind enemy radar, to drown the signal in noise, to render tracking impossible. In practice, they degraded tracking quality, but rarely broke lock entirely. The fan-song radar would maintain contact through the jamming, sometimes losing precision, but usually keeping enough fidelity to guide missiles to within lethal range. The bombers survived not because the jamming was effective, but because missile guidance wasn't perfect, because not every launch resulted in a kill, because probability favored the defender but didn't guarantee victory. Crenshaw found this unacceptable. Not morally unacceptable, though he certainly cared about crew survival, but intellectually unacceptable. The mathematics didn't work. The Americans were trying to outshout the enemy to transmit more power than the Soviet radar could receive. But the fan song was ground-based, connected to generators, effectively unlimited in power. The ALQ-87 ran on batteries, limited by weight constraints and power capacity. It was a losing equation. You couldn't win a power competition when the enemy controlled the power source. After his sixth mission, Crenshaw began spending his off-duty hours in the maintenance hangars, studying the ALQ-87 systems, reading technical manuals, talking to the technicians who serviced the equipment. He learned how the jammers worked at a component level: oscillators, amplifiers, antennas, power supplies. He learned their limitations, their failure modes, their theoretical maximum output. And he began to understand that the entire approach was flawed. The Americans were treating electronic warfare as a brute force problem: transmit more power, use more bandwidth, overwhelm the enemy's sensors with raw electromagnetic energy. It was the American way of war: substitute material superiority for strategic subtlety. But in this case, material superiority was an illusion. The jammers simply couldn't generate enough power to reliably blind the fan-song radar. Crenshaw had a different idea. Instead of blocking the radar signal, what if you could corrupt it? Instead of preventing the radar from seeing, what if you could make it see false information? The concept wasn't entirely new. Radar deception had existed since World War II. British bombers had dropped strips of aluminum foil to create false returns on German radar. American aircraft had used crude repeater jammers that received and retransmitted radar signals, creating ghost targets. But those systems were primitive, easily defeated by experienced radar operators who could distinguish between real and false returns. What Crenshaw envisioned was something more sophisticated: a system that could receive the enemy radar signal, analyze its characteristics in real time, and then transmit a false return signal that was perfectly synchronized with the real signal. Not noise, not chaff. A precise electronic lie that told the enemy radar, the aircraft is here, when in fact it was somewhere else. The technical challenges were enormous. The false signal had to match the frequency of the enemy radar exactly. It had to arrive at the radar receiver at precisely the right time. It had to have the correct phase relationship to the transmitted pulse. It had to be stronger than the real return from the aircraft. Otherwise, the radar would simply lock onto the real target. And it had to adjust continuously as the aircraft moved, maintaining the deception across the entire engagement. Crenshaw began sketching designs on yellow legal pads during the long afternoon hours when the heat made sleep impossible. He calculated signal strengths, delay times, phase shifts. He worked through the mathematics of radar deception, building equations that described how to convincingly lie to an electromagnetic sensor. The theory was solid. The implementation would be difficult. He needed parts. He needed test equipment. He needed time to build and debug a prototype. Most critically, he needed permission to modify combat equipment, to install unauthorized systems on operational aircraft. That permission would require approval from the Electronic Warfare Division at Wright-Patterson Air Force Base in Ohio, which would require submission of detailed technical specifications, which would require months of review, which would ultimately be denied because the system didn't meet safety certification standards and hadn't been validated through approved testing protocols. Crenshaw decided not to ask permission. Over the next 3 months, he became a ghost in the maintenance areas of Utapao. He worked during the dead hours between 2 and 6 in the morning, when most personnel were asleep and the flight line was relatively quiet. He cannibalized parts from damaged jamming pods awaiting repair. He requisitioned components under false paperwork, claiming they were needed for routine maintenance. He traded favors with maintenance technicians, trading his expertise in troubleshooting radar systems for their willingness to look the other way when he removed circuit boards from inventory. What emerged from his workshop was chaos given form a tangled mass of wires, breadboards, amplifiers, and antennas stuffed into a modified ALQ-87 housing. The device had 3 main sections. First, a receiving antenna and sensitive receiver that could detect fan-song radar pulses at long range. Second, a signal processing unit built from delay lines, phase shifters, and voltage-controlled oscillators that could analyze the received signal and generate a false return with precise timing and phase characteristics. Third, a high-power transmitter and directional antenna that could send the false signal back toward the enemy radar. The system worked through a process called coherent repeater jamming. When the fan-song radar transmitted a pulse, that pulse would strike Crenshaw's aircraft and reflect back naturally, creating a legitimate radar return. But a fraction of a second before that natural reflection reached the radar receiver, Crenshaw's jammer would transmit its own pulse, a false return that mimicked the characteristics of the real one but arrived earlier. The enemy radar, receiving 2 signals, would lock onto the stronger one. Because Crenshaw's transmitter was more powerful than the natural reflection, the radar would lock onto the false return. Then the magic happened. By varying the delay between receiving the fan-song pulse and transmitting the false return, Crenshaw could make his aircraft appear to move on the enemy radar screen. Increase the delay slightly, and the false return arrived later, making the aircraft appear farther away. Decrease the delay, and it appeared closer. By systematically modulating the delay, he could make the bomber appear to drift left or right, climb or descend, accelerate or decelerate. The real bomber would be flying straight and level, but the radar would track a ghost that moved according to whatever flight path Crenshaw's electronics generated. Better yet, he could cut the transmission entirely for brief moments. When the false return disappeared, the radar would briefly reacquire the real aircraft. But before it could establish solid lock, the false return would reappear, stronger than before, pulling the tracking solution back to the ghost. To the radar operator, it would look like the aircraft was experiencing intermittent fading, a common phenomenon caused by atmospheric conditions. He would trust his equipment and continue tracking the false target, never realizing he was chasing an electronic phantom. On paper, the system was brilliant. In reality, it had never been tested in combat. It had never been tested at all, except on a bench in a maintenance hangar at 3 in the morning, using a borrowed test radar as a target. Crenshaw had no idea if it would work against a real fan-song radar being operated by a trained Soviet technician in combat conditions. He had no idea if the timing would be accurate enough, if the phase synchronization would hold, if the power output would be sufficient. He had no idea if it would interfere with the bomber's other systems, if it would create electromagnetic interference that disrupted navigation or communication or flight controls. He had no idea if it would save lives or get everyone killed. The only way to find out was to fly it in combat, which required finding a crew willing to install unauthorized equipment on their aircraft and fly a mission with a device that might not work, might malfunction, might actively make them a better target. Crews were superstitious. They liked routine, predictability, systems they trusted. Asking them to fly with an illegal modification built by a captain working in secret was asking them to violate every instinct that kept them alive. Crenshaw needed someone desperate enough to try. Major Robert Keyes was desperate. Not personally desperate, he was a professional, a career officer, a pilot with over 3,000 hours in heavy bombers. But he was desperate in the way that all combat aircraft commanders become desperate when they watch friends die and can do nothing to prevent it. He'd arrived at Utapao in November 1971, just in time for the escalation of bombing operations that would culminate in Linebacker II. His first mission was a night strike against a truck park in Laos, relatively safe, lightly defended, good for breaking in a new crew. His second mission was against a petroleum storage facility north of Hanoi, and he watched a B-52 3,000 feet to his right disintegrate when an SA-2 detonated close enough to sever the tail section. The bomber tumbled out of formation, broke apart, fell 25,000 feet, trailing burning fuel. He counted 4 parachutes. The crew was 6 men. Over the next 13 months, Keyes flew 38 combat missions. He developed the nervous habits that all combat pilots develop, checking and rechecking systems, running through emergency procedures in his mind, calculating bailout options for every phase of flight. He learned to trust his equipment but not depend on it. He learned to trust his crew but know that trust couldn't stop missiles. He learned that probability eventually catches everyone, that survival was partly skill and partly luck, and that the luck part was beyond any crew's control. The ALQ-87 jamming pods were supposed to improve the luck part. They were supposed to degrade enemy radar, make tracking difficult, reduce the probability of a successful missile engagement. Sometimes they worked, sometimes they didn't. Keyes couldn't identify a pattern. Some missions, the jamming seemed effective. The missile warning systems would track SA-2 launches, but the missiles would detonate far enough away to be merely frightening rather than lethal. Other missions, the missiles would track through the jamming as if it wasn't there, detonating close enough to pepper the aircraft with shrapnel, close enough to rattle the crew's nerves and make them question whether tonight was the night their luck ran out. By December 1972, Keyes had developed a philosophy about electronic warfare equipment. It was better than nothing, but not much better. The jammers gave the crew something to do, something to operate, the illusion of control. But Keyes suspected that survival had less to do with jamming effectiveness and more to do with random chance, whether the enemy radar operator was experienced or green, whether the missile guidance system was properly calibrated, whether atmospheric conditions favored or hindered tracking. He'd heard rumors about a captain working on some kind of new jamming system. Maintenance personnel talked about someone requisitioning unusual parts, someone working odd hours in the equipment bays. Keyes didn't pay much attention. The Air Force was always working on new systems, new countermeasures, new solutions. Most of them never made it out of development. The ones that did usually worked marginally better than what they replaced, which meant they worked marginally better than barely adequate. Then Crenshaw approached him in the hallway outside the briefing room. The conversation lasted 4 minutes. Crenshaw was direct, almost blunt. He'd built a new type of jammer. It was unauthorized. It hadn't been tested in combat. It violated about a dozen regulations regarding equipment modification and use of unapproved systems. But it might work better than the ALQ-87. It might significantly improve their chances of surviving missions over Hanoi. Was Keyes interested? Keyes asked the only question that mattered. Can you install it tonight? Crenshaw could. The installation took 6 hours. Crenshaw and 2 maintenance technicians he'd recruited removed one of the existing ALQ-87 pods from the B-52's wing pylon and replaced it with his modified version. The external dimensions were identical, the modified pod fit the mounting points perfectly, but the internal electronics were completely different. Crenshaw ran diagnostic checks, verified that the system powered up correctly, tested the receiver sensitivity. Everything checked out, as well as could be expected for a device that had never flown before. Keyes watched the installation from a distance, smoking cigarettes in the darkness beyond the work lights. He was violating regulations. If the mission went badly, if the jammer interfered with critical systems, if someone was killed because of unauthorized equipment, he would face court-martial. His career would be over. Possibly his freedom, depending on how aggressive the prosecutors wanted to be. But men were dying. The approved systems weren't working well enough. And Keyes had reached a point in his combat tour where the prospect of court-martial seemed less frightening than the prospect of watching another crew member die because inadequate equipment had failed at a critical moment. At 0300 hours, Crenshaw signed off on the installation. The modified pod was armed and ready. Keyes thanked him, walked to the operations building, and briefed his crew on the night's mission. He didn't mention the modified jammer. What they didn't know couldn't make them nervous. Mission number 41. Target: rail yard north of Hanoi. Expected defenses: heavy. SA-2 coverage: extensive. Weather: clear. Moon: waning crescent. Probability of successful strike: high. Probability of encountering enemy fire: 100%. The B-52 rolled down Utapao's runway at 0430 hours, engine screaming, 60,000 pounds of fuel and 40,000 pounds of conventional bombs straining against gravity and inertia. Keyes felt the familiar sensation of rotation, the moment when the aircraft transitioned from ground vehicle to aircraft, when physics took over and height became life. The bomber climbed through humid tropical air, banking slowly toward the northeast, joining formation with 11 other B-52 seconds that would make the 3-hour flight to North Vietnam as a single strike package. Inside the aircraft, 6 men performed the rituals of combat aviation. The co-pilot monitored engine instruments, watching temperatures and pressures and fuel flow rates. The navigator worked his calculations, plotting course corrections, updating time to target estimates. The radar navigator operated the bombing systems, preparing the release sequence, checking and rechecking coordinates. The electronic warfare officer monitored threat receivers, cataloging enemy radar emissions, preparing countermeasures. The gunner watched the tail radar, scanning for interceptors. They flew in darkness over eastern Thailand, crossing into Laos at 0500 hours. Below, jungle stretched to the horizon, broken occasionally by rivers that gleamed silver in starlight. American aircraft had been flying over this landscape for 8 years, bombing trails and supply routes and suspected enemy positions. The ground was cratered, scarred, transformed by high explosives into something that barely resembled terrain. But the war continued. The trucks kept moving south, the supplies kept flowing, and American bombers kept flying north, into the teeth of the most sophisticated air defense network ever created. At 0600 hours, they crossed into North Vietnamese airspace. The electronic warfare officer reported multiple radar emissions, search radars at first, sweeping the sky for targets, then tracking radars as the air defense network acquired the formation. The SA-2 sites were waking up, operators reaching for their controls, missile batteries rotating toward intercept bearings. The mathematics of death, calculated in dozens of locations simultaneously. Keyes felt his stomach tighten. It always did at this point in the mission, the moment when commitment became irrevocable, when retreat stopped being an option. They were flying toward Hanoi now, toward the most heavily defended city in the world, defended by missiles that could kill at 40 miles and radars that could see at 100. The approved plan was to rely on jamming, on formation integrity, on the hope that statistical probability would favor someone else. Tonight, Keyes was relying on an unauthorized device built by a captain who'd promised nothing except that it might work. At 30,000 feet, the first SA-2 rose from a site near Yanbai. The electronic warfare officer called it out. Missile launch, 10 o'clock, 20 miles. Then another. Then 6 more. A ripple launch from multiple sites, filling the night sky with pillars of flame. The missiles climbed toward the formation, adjusting trajectory, correcting for wind and altitude, and the predicted flight path of their targets. Keys maintained course and speed. Breaking formation would make them vulnerable to fighters. The approved doctrine was to trust the jamming, trust the formation, trust that the missiles wouldn't track perfectly through the countermeasures. It was doctrine written by people who didn't fly combat missions over Hanoi. The electronic warfare officer activated the jamming systems. The ALQ-87 pods, both the legitimate ones on the other wing and Crenshaw's modified version, powered up, transmitting electromagnetic energy into the night. But Crenshaw's system did something different. Instead of simply broadcasting noise, it listened first. The modified receiver detected the fan-song radar pulse washing over the bomber. The signal processing unit analyzed its characteristics, frequency, pulse width, pulse repetition rate. Then, in the microsecond before the natural radar return from the bomber reached the enemy receiver, Crenshaw's transmitter sent back a carefully crafted lie. What happened next was invisible to Keyes and his crew but apocalyptic to the radar operators below. At Site 47, northeast of Hanoi, Senior Lieutenant Petrov had achieved solid lock on Keyes's bomber. The tracking solution was perfect range, altitude, velocity all confirmed, updating continuously. He designated the target as Priority 1, verified that his missiles were armed and ready. The engagement solution showed 93% probability of kill. 2 SA-2 seconds had left their launchers, climbing toward intercept on pillars of fire. The mathematics were perfect. The missiles could not miss. Then his target split, not faded, not degraded, split. The single radar return became 2 distinct echoes, identical in every characteristic except position. One echo continued on the original trajectory. The second echo drifted left, slowly at first, then faster, until it was tracking a course 10 degrees off the original bearing. Petrov's tracking computer attempted to follow both returns, couldn't reconcile the contradictory data, made a choice based on signal strength, locked onto the stronger return, which was the false one, the ghost, the electronic lie being transmitted by Crenshaw's modified jammer. The missiles, now guided by Petrov's tracking solution, adjusted their trajectory to intercept the false return. They climbed toward where Crenshaw's jammer told them the bomber would be, but the bomber wasn't there. It was 2,000 feet lower and half a mile to the right, flying serenely through sky that the missiles had already passed. The SA-2 seconds reached their calculated intercept point, found nothing, detonated anyway. Their warheads transformed into expanding spheres of shrapnel that shredded empty air. Inside Keyes's B-52, the crew felt the concussion. The aircraft shuddered as pressure waves from the detonations passed through it. The gunner reported explosions close aboard, maybe 3,000 feet, maybe less. But no impact, no damage. The bombers pressed on, maintaining formation, the mission clock counting down to bomb release. Petrov stared at his radar screen and tried to understand what had happened. His missiles had detonated. He'd received the telemetry confirming warhead function, but the target was still there. Still tracking, still intact. Worse, it was now showing in a different position than where his guidance solution had predicted. Had he miscalculated? Was his tracking solution wrong? He'd performed identical intercepts dozens of times. The mathematics had always worked. He attempted to reacquire lock. His radar swept across the American formation, painting returns from multiple bombers. He selected the same target again, began building a new firing solution. This time he watched more carefully, monitoring the quality of the return signal, looking for any indication of jamming or interference. The return was clean, strong, high confidence. The tracking solution built smoothly, showing range and bearing and altitude with precision that seemed unquestionable. He launched again. 2 more SA-2 seconds climbed into the darkness, guided by what his radar told him was perfect tracking data. The missiles corrected course, adjusted altitude, homed on the target that Petrov's screen showed with crystalline clarity. And then the target vanished entirely. Not faded, vanished. One moment the radar return was solid and strong. The next moment there was nothing. Blank sky. Empty screen. His missiles, now unguided, continued on their last known trajectory for a few seconds before their proximity fuses activated, and they detonated harmlessly. Petrov cycled through his frequencies, adjusted his gain, checked his equipment diagnostics. Everything showed normal. The radar was functioning perfectly, but it was seeing things that couldn't be real. Or more accurately, it was failing to see things that should be there, then seeing things in impossible locations. 3 seconds later, the target reappeared. But now it was 5 miles from where it had vanished, at a different altitude, tracking a different course. The same bomber, the same radar signature. But the position made no sense. A B-52 couldn't move 5 miles in 3 seconds. Physics didn't permit it. Unless the Americans had found a way to inject false data into his tracking solution. Unless they were making his radar see things that weren't there. Unless every return signal, every echo, every piece of tracking data his sophisticated Soviet equipment was showing him was a carefully crafted lie. Petrov felt something cold settle into his stomach. He'd been an electronics officer for 12 years. He understood radar theory the way a concert pianist understands music theory. He knew what was possible and what wasn't. What he was seeing wasn't possible, but he was seeing it anyway. Around him, the bunker had descended into controlled chaos. Other sites were reporting similar anomalies. Targets that multiplied, returns that vanished and reappeared, tracking solutions that made no sense. The North Vietnamese Air Defense Commander was screaming into multiple phones simultaneously, demanding explanations, demanding that someone shoot down the Americans who were now approaching their targets with apparent impunity. More missiles launched. Dozens of them. A barrage fired more in frustration than with any real hope of success. Some were guided by radar that was tracking ghosts. Some were fired blind, simply lobbed into the known bombing corridors with the hope that probability would put a missile close enough to an American bomber to score a kill. The night sky lit up with launches, turning darkness into something that resembled daylight, creating a spectacle that would have been beautiful if it wasn't so deadly. And through it all, the American bombers pressed on, apparently oblivious to the chaos they'd created below, flying steady courses toward their targets while Soviet radar operators watched their screens and tried to understand what had gone wrong. Inside Keyes's B-52, the electronic warfare officer was reporting missile launches in a voice that had taken on a slightly confused edge. Multiple launches. Tracking radars are active, but I'm not seeing solid lock. I don't know, sir. The tracking doesn't look right. The missiles are detonating early. Way early. Like they're chasing bad data. Keyes said nothing. He couldn't explain what was happening without revealing the unauthorized modification. But he understood. Crenshaw's jammer was working. It was working better than anyone had hoped. The Fansong radars weren't being blinded. They were being deceived. They were tracking targets that didn't exist, guiding missiles to intercept points where no bombers would be. It was elegant. It was brilliant. It was saving their lives. The radar navigator called out bomb release in 30 seconds. The formation tightened slightly, each bomber adjusting position to ensure maximum concentration of ordnance on target. The rail yard below had no idea what was about to happen. North Vietnamese air defense was so focused on trying to shoot down the bombers that no one had thought to warn the people on the ground. Bombs away. 40,000 pounds of high explosive falling from 30,000 feet, accelerating under gravity, following ballistic trajectories that had been calculated with slide rules and bombing tables, and the accumulated experience of 3 decades of strategic bombing doctrine. The bombs took 40 seconds to fall. The B-52 seconds turned for home, banking away from Hanoi, heading back toward Laos and Thailand and safety. Behind them, the rail yard erupted. Explosions marched across the facility in sequence, each detonation creating a crater, throwing debris hundreds of feet into the air. setting fires that would burn for hours. Rolling stock was obliterated. Rail lines were torn apart. Fuel tanks ruptured and ignited, adding their own contribution to the inferno. The mission objective had been achieved with precision that would have made Curtis LeMay proud. But Keyes was more interested in the flight home. They were still over North Vietnam, still in range of SA-2 sites, still vulnerable. The electronic warfare officer reported tracking radars following them, missile sites preparing to engage. More SA-2 seconds launched, trying to hit the bombers as they withdrew, and every single one failed to track correctly. The missiles climbed, corrected their courses toward intercept points that Crenshaw's jammer told them were correct, arrived at those points to find empty sky, and detonated harmlessly. It was a 3-hour flight back to Utapao. 3 hours of wondering if the jammer would continue working, if the Soviets would figure out what was happening and adapt, if some random failure in Crenshaw's breadboard electronics would leave them suddenly vulnerable. But the modified system operated flawlessly. Every time a fan-song radar painted their aircraft, Crenshaw's device received the signal, processed it, transmitted a false return that pulled the tracking solution away from the real bomber. They landed at Utapao at 0900 hours, wheels touching down on the same runway they'd departed from 5 hours earlier. The post-mission debrief was strange. Keyes reported the mission as successful, target destroyed, no damage to aircraft, unusually ineffective enemy air defenses. The intelligence officer asked questions about the SA-2 launches, about why so many missiles had detonated far from the formation. Keyes said he didn't know. Poor missile guidance, maybe. Atmospheric conditions. Luck. He didn't mention the modified jammer. Not yet. He wanted to fly it again, to verify that the first mission wasn't a fluke, to build data that would be undeniable when the time came to explain what they'd done. Over the next 11 days, Crenshaw's jammer flew 18 more missions. Each time, the results were similar. Missiles failed to track correctly. Radar locks degraded or broke entirely. The bomber returned safely while other aircraft in the formation took hits, suffered damage, sometimes went down. The disparity became noticeable. Maintenance crews began asking why Keyes's bomber seemed charmed, why it never took battle damage, why the missile warning systems showed fewer close approaches than other aircraft. Word spread quietly through the squadrons. Pilots talked in low voices in the officers' club, sharing observations, comparing notes. Some aircraft came back with shrapnel damage, hydraulic leaks, electrical failures. Keyes's bomber came back untouched, night after night, mission after mission. The probability of that happening by chance was vanishingly small. Then someone noticed the modified pod. A sharp-eyed maintenance officer who'd been trained to spot unauthorized modifications, who understood that equipment on operational aircraft was supposed to match technical specifications exactly. He reported it up the chain of command. The report triggered an investigation. The investigation led to Crenshaw. The interview took place in a windowless office at Utapao, conducted by a lieutenant colonel from the Inspector General's office who'd flown in from Saigon specifically to investigate unauthorized equipment modifications. The charges were serious: violation of procurement regulations, circumvention of safety certification requirements, installation of unapproved systems on operational aircraft, use of equipment that hadn't been tested or validated, potential endangerment of aircrew through use of unverified systems. Crenshaw didn't deny anything. He walked the investigators through his design, explained the theory behind coherent repeater jamming, showed them his calculations and circuit diagrams. He was calm, methodical, utterly professional. He explained that the approved jamming systems weren't working adequately, that loss rates were unacceptable, that crews were dying because existing countermeasures couldn't defeat the fan-song radar. The investigators weren't impressed. Regulations existed for good reasons. Safety certification prevented the installation of equipment that might interfere with critical systems. The approval process ensured that modifications were thoroughly tested before being deployed in combat. Crenshaw had bypassed all of that, substituting his own judgment for institutional wisdom accumulated over decades of military aviation. But the data was undeniable. The investigators pulled mission reports, compared loss rates, analyzed battle damage assessments. Aircraft equipped with conventional jamming systems, 12% loss rate over heavily defended targets. Keyes's aircraft with Crenshaw's modified jammer, 0 losses over 19 missions. The statistics were stark. The investigators requested technical analysis from Wright-Patterson Air Force Base. They sent Crenshaw's circuit diagrams, his calculations, his theory of operation. Engineers in Ohio studied the design, ran simulations, evaluated the concept. Their conclusion: the system was theoretically sound. The coherent repeater approach should work exactly as Crenshaw claimed. The implementation was crude, built from cannibalized parts and breadboard circuits, not suitable for production. But the concept was valid. More importantly, the concept was revolutionary. The engineers at Wright-Patterson had been working on jamming systems for years, trying to develop more powerful transmitters, wider bandwidth coverage, faster frequency switching. They'd been focused on the brute force approach, on overwhelming enemy radar with noise. Crenshaw had taken a completely different direction. Instead of blocking the signal, he'd corrupted it. Instead of preventing the radar from seeing, he'd made it see false information. The implications were staggering. If this approach could be refined, productionized, deployed at scale, it could render Soviet air defense radar largely ineffective, not just the fan song. Any radar system that relied on coherent signal processing could potentially be deceived by well-designed repeater jammers. The entire architecture of Soviet air defense built around radar-guided missiles and radar-directed interceptors would become questionable. The investigation concluded with recommendations that were very military and very much a product of the institutional Air Force. Crenshaw received an official reprimand for violating equipment modification regulations. The reprimand went into his personnel file, a permanent mark that would affect promotion boards, that would follow him for the rest of his career. He was removed from flight status pending review. His modified jammer was confiscated and shipped to Wright-Patterson for detailed analysis. And then, quietly, the Air Force began incorporating his ideas into official development programs. The ALQ-99 tactical jamming system, designed for the EA-6B Prowler electronic warfare aircraft, included coherent repeater capabilities based directly on Crenshaw's work. The ALQ-131 jamming pod, which would become standard equipment on F-15 and F-16 fighters, used phase-synchronous deception techniques that Crenshaw had pioneered. The concept of radar deception, of making enemy sensors see false targets rather than trying to blind them entirely, became foundational to American electronic warfare doctrine. Crenshaw's name appeared nowhere in the official development history. His contribution remained classified, buried in technical reports that few people had clearance to read. But pilots who flew with the new systems, who discovered that Soviet radars suddenly seemed less capable, who found themselves surviving missions that should have been fatal, owed their lives to an engineer who'd broken rules because following them was getting people killed. The war ended in January 1973. The Paris Peace Accords were signed. American forces began withdrawing from Southeast Asia. The bombers went home. The radar sites were abandoned or dismantled. The SA-2 missiles were shipped back to the Soviet Union or left to rust in the jungle. The men who'd fought the electronic warfare battle engineers and operators on both sides returned to peacetime duties, carrying with them knowledge that would shape military technology for decades. Viktor Petrov wrote his report about the night American bombers vanished from his radar screen. The report was classified, analyzed by Soviet engineers, incorporated into research programs designed to counter American electronic warfare capabilities. The Soviets never quite solved the problem. They built more sophisticated radars with better signal processing, with frequency hopping, with multiple receiver arrays that could triangulate target positions. But the fundamental vulnerability remained. If an adversary could precisely mimic your radar signal and transmit it back to you with the right timing and phase characteristics, they could make you see whatever they wanted you to see. The Fansong radar continued in service with air defense forces around the world for another 2 decades. but it never regained the fearsome reputation it had earned in the skies over Vietnam. American electronic warfare systems had evolved to counter it, to deceive it, to render it unreliable. In the 1982 Lebanon War, Israeli aircraft equipped with advanced jamming pods flew through Syrian air defenses that included Fansong radars and SA-2 missiles. The Syrians launched 86 missiles and scored 0 kills. The Fansong operators watched their screens and saw targets that weren't there, tracked aircraft that were miles from where the radar indicated, fired missiles that chased electronic ghosts into empty sky. The technology that made this possible traced its lineage directly back to a maintenance hangar at Utapao, to a captain working through the night with a soldering iron and a conviction that the approved solutions were inadequate. Paul Crenshaw's career in the Air Force ended earlier than it might have otherwise. The official reprimand in his file created friction with promotion boards. He made major but never lieutenant colonel. He transferred to reserve status in 1978 and took a job with a defense contractor working on classified electronic warfare programs. The work was interesting, the pay was better, and he could design systems without worrying about court-martial. He never spoke publicly about his unauthorized jammer. The classification would remain in effect for decades. But in certain circles, among electronic warfare officers, among engineers who worked on radar deception systems, among the institutional memory of the Air Force's electronic warfare community, his name became legend. The guy who'd built a ghost maker in a Thai hangar. The guy who'd figured out how to lie to Soviet radar. The guy whose illegal modification had worked better than any approved system. In the 1,990 seconds, when the Air Force began developing the F-22 stealth fighter, the engineers working on radar cross-section reduction had access to decades of research into making aircraft invisible to radar. Some of that research involved physical design, shaping the aircraft to minimize reflections, coating surfaces with radar-absorbent materials. But some of it involved active electronic countermeasures, systems that could detect enemy radar and respond with precisely calibrated signals designed to corrupt tracking solutions. The lineage was clear to anyone who studied the history. Crenshaw's coherent repeater concept had evolved into sophisticated electronic warfare suites that could generate false targets, create ghost formations, make a single aircraft appear to be multiple aircraft, or multiple aircraft appear to be one. The technology was exponentially more advanced than anything Crenshaw had built in 1972. It was production quality, thoroughly tested, integrated into aircraft systems from the design phase. It bore no physical resemblance to the breadboard circuits stuffed into a modified ALQ-87 housing, but the underlying principle remained the same. Don't block the enemy's radar. Make it see what you want it to see. In 2003, 30 years after the end of the Vietnam War, the Air Force declassified portions of the Linebacker II after-action reports. Historians began piecing together the story of the Christmas bombing campaign, the tactics, the losses, the effectiveness of various weapon systems. Some of the reports mentioned unusual electronic warfare effects, references to anomalous tracking failures, and apparent radar deception capabilities. A few researchers tried to track down more details. They submitted Freedom of Information Act requests for technical specifications of jamming systems used during Linebacker II. Most of the requests were denied. The systems remained classified even 30 years later, apparently still sensitive enough that the Air Force didn't want details made public. One researcher, more persistent than most, managed to obtain heavily redacted documents describing experimental electronic countermeasure systems tested in combat during December 1972. The documents confirmed that unauthorized modifications had been made to operational aircraft. They noted that these modifications, while technically in violation of regulations, had demonstrated effectiveness superior to approved systems. They recommended that the techniques be incorporated into official development programs. The name of the engineer who'd built the system was redacted. So was the technical description of how it worked. But the pattern was clear enough for anyone familiar with electronic warfare history. Someone had built a radar deception system. Someone had flown it in combat without permission. And it had worked well enough that the Air Force had quietly adopted the technology while officially reprimanding the person who'd created it. That's how innovation often happens in warfare. Not through careful planning and institutional foresight, but through individual initiative, through people who see problems that need solving and solve them regardless of whether they have permission. The military services try to balance this creative tension, encouraging initiative while maintaining the discipline and standardization that large organizations require. Sometimes they succeed. Sometimes they punish the innovators and steal their ideas. Crenshaw's story is both. He was punished with a reprimand that limited his career advancement. His invention was confiscated and classified, but his ideas were incorporated into systems that saved countless lives over the following decades. The Air Force couldn't publicly acknowledge what he'd done, couldn't admit that an unauthorized field modification had succeeded where approved programs had failed. But they could, quietly, learn from what he'd accomplished. There's a broader lesson here about the nature of military technology and institutional adaptation. The United States, for all its vast defense budget and sophisticated research programs, doesn't have a monopoly on innovation. Adversaries adapt, they learn, they develop countermeasures. The fan-song radar that seemed so invincible in 1965 was vulnerable by 1972. Not because the radar had changed, but because American engineers had figured out its weaknesses. But Soviet engineers learned too. They analyzed American jamming techniques, developed new radar systems that were harder to deceive, created missiles that could home on jamming signals. The competition never ended. Each innovation triggered a counter-innovation. Each new capability was met with a new countermeasure. Electronic warfare became an endless race, where standing still meant falling behind. The race continues today. Modern military aircraft carry electronic warfare suites that would seem like science fiction to the engineers of the 1,970 They can detect enemy radar at hundreds of miles, analyze signal characteristics in real time, generate precisely tailored countermeasures automatically. They can create ghost formations, false targets, phantom aircraft that exist only as electromagnetic echoes. The technology is classified, sophisticated, integrated into every aspect of modern air combat. But the fundamental principle that deception beats power, that a clever lie is more effective than a loud truth, traces back to a captain in a Thai hangar, building circuits by hand because the approved solutions weren't good enough. December 2002. 30 years after Linebacker II. A ceremony at Eglin Air Force Base in Florida, home of the Air Force's electronic warfare community. The occasion is the retirement of a senior electronics engineer who'd worked on classified systems for 3 decades. Dozens of people attend, former colleagues, military officers, defense contractors. The retiree gives a brief speech, thanking everyone, making the kind of modest remarks that engineers make when they're being honored. Afterward, in informal conversations, someone mentions Linebacker II. Someone else brings up the unauthorized jammer that had supposedly been used during the Christmas bombing campaign. The stories have taken on mythical qualities over the years, growing in the telling, becoming legends that may or may not reflect reality. An older man listening to the conversation speaks up. He's in his 70s, gray-haired, unremarkable in appearance. He says he was there in 1972. He says he built something in Thailand that flew on B-52 seconds during Linebacker II. He says it worked better than anyone expected. The conversation stops. People turn to look at him. Someone asks if he's Paul Crenshaw. He smiles and doesn't answer directly. The reprimand is still in his official file, though his career is long over. The classification is still in effect on some of the technical details. But he confirms that yes, there was an unauthorized jammer. Yes, it used coherent repeater techniques. Yes, it saved lives. And yes, he'd do it again, regulations or no regulations. Because watching friends die, while bureaucrats argued about procurement procedures, was not something he could accept. Later, someone would write up the conversation and submit it to an Air Force historical journal. the article would be rejected as unverifiable. The declassification process was incomplete. The technical details were still sensitive, and the Air Force remained unwilling to officially acknowledge that unauthorized modifications had been used on combat aircraft. But the story persisted in oral tradition, in the collective memory of the electronic warfare community, in the knowledge that sometimes the most important innovations come from people who refuse to accept that the approved answer is adequate. Crenshaw, if that was indeed the man at the ceremony, returned to obscurity afterward. No interviews, no memoirs, no detailed technical papers. If he'd kept notes, or diagrams, or documentation of his work in Thailand, he never made them public. The knowledge stayed classified, locked away in archives that most people would never access. But the legacy was visible to anyone who understood where to look. In the electronic warfare pods hanging under fighter wings, in the sophisticated radar, warning receivers that could detect threats at extreme range, in the doctrine that taught young pilots that electronic combat was as important as kinetic combat, in the understanding that making the enemy see false information was often more valuable than preventing them from seeing anything at all. The ghost maker had vanished into history, leaving behind only ghosts, electronic phantoms that flew through enemy radar screens, phantom targets that pulled missiles away from real bombers, phantom innovations that the Air Force couldn't officially acknowledge but couldn't function without. Return to Hanoi, December 1972. The concrete bunker where Viktor Petrov sits and watches his radar screen show impossible things. The American bombers have passed. The raid is over. The damage assessment will come later: destroyed rail yards, burning fuel depots, casualties that will be counted in the morning. But right now, in this moment, Petrov is alone with his equipment and his thoughts. He runs diagnostics on his Fansong radar. Everything checks out. The system is functioning perfectly, exactly as designed, exactly as it has functioned through hundreds of successful intercepts. The problem isn't with the equipment. The problem is that the Americans have learned to exploit the equipment's fundamental assumptions. The radar assumes that returns are honest, that echoes represent real objects, that the electromagnetic signals bouncing back to the receiver are truthful reports about what exists in the sky. The Americans have learned to lie to it, to inject false information that the radar cannot distinguish from truth, to corrupt the data at such a fundamental level that no amount of signal processing can separate real from fake. Petrov understands what this means. He understands that radar, the technology that defined air defense for 3 decades, that seemed like an unbeatable sensor, that had made the sky transparent to defenders, has a vulnerability that cannot be easily fixed. You can make radars more powerful, more sensitive, more sophisticated. But if an adversary can precisely mimic your signal and feed it back to you with the right timing, they can make you see whatever they want. The solution would require completely different approaches to air defense, maybe optical tracking systems that can't be jammed, maybe infrared sensors that detect heat rather than reflecting signals, maybe passive listening systems that locate aircraft by their electromagnetic emissions. The Soviets will pursue all of these paths over the coming decades, trying to build air defense networks that aren't vulnerable to the deception techniques the Americans have pioneered. But tonight, Petrov simply sits in his bunker and accepts that the war has changed. The Americans have stopped playing by the established rules. They've found an asymmetric advantage, a way to render sophisticated Soviet technology partially obsolete without building anything more powerful, just something more clever. In the distance, he can hear fire trucks responding to the bombs that fell on Hanoi. The sounds of war, mechanical and human, blend into a background noise that has become so constant he barely notices it anymore. The war will continue. More bombers will come. More missiles will launch. More men will die on both sides. But the certainty that technology provides advantage, that better sensors inevitably lead to military success, has been shaken. A North Vietnamese officer enters the bunker, demands to know what happened, why the missiles didn't track correctly, why the Americans were able to strike their target with apparent impunity. Petrov tries to explain about electronic deception, about false returns, about the impossibility of distinguishing between real targets and sophisticated false signals. The officer doesn't want technical explanations. He wants results. Petrov promises to adjust his tactics, to be more cautious about trusting radar returns, to manually verify tracking solutions before launching missiles. He knows these adjustments won't solve the underlying problem. The Americans have found a fundamental vulnerability in how radar works. You can't fix fundamental vulnerabilities with tactical adjustments. The officer leaves, unsatisfied, but having no better options. Petrov remains at his console, watching his radar sweep the empty sky, thinking about the bombers that vanished from his screen, wondering what other surprises American engineers have prepared. The fan-song radar continues its rotation, painting the world in electromagnetic echoes, faithfully reporting everything it sees. But Petrov no longer fully trusts what it shows him. That trust, once broken, can never be completely restored. And without trust in sensors, air defense becomes guesswork. Educated guesswork, trained guesswork, but still fundamentally uncertain. The Americans have weaponized uncertainty, have turned it into a tool as effective as any bomb or missile. In the morning, Petrov will write his report. He will use careful technical language to describe advanced electronic countermeasures and sophisticated deception capabilities. His report will be forwarded to Moscow, where Soviet engineers will study it and begin urgent research programs to understand and counter the American techniques. Some of those engineers will eventually develop effective countermeasures. But by that time, American engineers will have developed new deception methods, more sophisticated techniques, better ways to lie to sensors. The race will never end. Each advance triggers a counter-advance. Each innovation spawns a counter-innovation. Electronic warfare becomes an endless competition where advantage is always temporary, where today's breakthrough is tomorrow's baseline that must be exceeded. The only constant is change. The only certainty is that certainty is impossible. Petrov lights a cigarette, blowing smoke toward the concrete ceiling, watching it swirl in the dim light. He's a good engineer, a competent operator, a professional who understands his equipment at a deep technical level. But he's just one man, operating one radar, defending one small piece of airspace in a war that spans an entire country. The Americans have thousands of engineers, unlimited resources, institutional support for innovation. They can afford to experiment, to fail, to try new approaches until something works. The Soviet Union has engineers too, of course, talented ones. The fan-song radar was itself a marvel of engineering when it was designed. But Soviet military technology follows a different path, more centralized, more focused on proven approaches, less tolerant of unauthorized innovation. The idea of a single engineer secretly building an unauthorized system and flying it in combat without permission would be unthinkable in the Soviet air defense forces. Such initiative would be punished severely. The system values discipline over creativity, standardization over experimentation. Maybe that's the real advantage the Americans have. Not better technology, not more resources, but a military culture that sometimes tolerates innovation even when it breaks rules, that occasionally allows individual initiative to override institutional procedures, that accepts calculated risks when the alternative is accepting unacceptable losses. Petrov doesn't think in those terms. He's not a philosopher or a military strategist. He's an electronics officer who operates radar systems and guides missiles and does his job as well as his training and equipment allow. But somewhere in the back of his mind, he understands that the Americans who vanished from his screen tonight weren't just lucky. They weren't just skilled. They had something new, something his training hadn't prepared him for, something that gave them an edge that Soviet doctrine couldn't counter. The war will end eventually. The Americans will go home, the radar sites will be dismantled. And Petrov will return to the Soviet Union, carrying with him the memory of the night American bombers became ghosts, the night his sophisticated equipment showed him impossible things, the night he learned that technology is never permanent, advantage is never secure, and in the contest between sensors and countermeasures, the countermeasures had just scored a decisive victory. The final word belongs to the pilots. The men who flew through the night sky over Hanoi, who watched missiles climb toward them, who trusted their equipment to keep them alive. Most of them never knew about Crenshaw's unauthorized jammer. They flew their missions, relied on their training, trusted that the electronic warfare systems would work as advertised. Some noticed that certain aircraft seemed to attract less fire than others. Some observed that missile tracking seemed less accurate on some missions than others. But combat is chaotic, and it's impossible to isolate variables when you're flying through a sky full of surface-to-air missiles. Maybe it was luck. Maybe it was skill. Maybe it was atmospheric conditions, or enemy incompetence, or simple random chance. Only a few knew the truth. Knew that one crew had been flying with a device that shouldn't have existed, that violated regulations, that had never been officially tested. And that device had worked when approved systems failed, had saved lives when institutional solutions proved inadequate. In later years, some of those pilots would be asked what they thought about unauthorized modifications to combat aircraft. The question was usually hypothetical, part of safety training or regulatory review. The official answer was clear. Unauthorized modifications are dangerous, can compromise safety, must never be permitted. But among themselves, in conversations that happened late at night in officers' clubs after too many drinks, the pilots sometimes told a different story, about a captain who built something in secret, about a crew that flew it in combat without permission, about missions where missiles detonated early, tracking radars lost lock, and bombers came home when probability said they shouldn't. They never named names. The classification remained in effect, but they told the story anyway, because it deserved to be told, because innovation deserves recognition even when regulations forbid it, because sometimes the most important breakthroughs come from people who refuse to accept that following rules is more important than saving lives. In a war fought with bombs and missiles and overwhelming material force, one engineer's forbidden signal was more powerful than any weapon. It didn't destroy targets. It didn't kill enemy soldiers. It simply made American bombers harder to kill, harder to track, harder to engage. It gave crews a chance to come home, gave missions a higher probability of success, gave the Air Force capabilities it didn't know it needed until someone built them anyway. That's the legacy. Not official recognition or public acknowledgement, not promotions or medals or historical monuments, just the quiet knowledge that when approved solutions weren't good enough, someone had the courage and skill and determination to build something better, even if it meant risking everything. The ghosts were real. The ghosts saved lives. And the ghosts changed warfare forever. In the decades that followed, electronic warfare evolved into something Crenshaw and Petrov and the crews who flew over Hanoi could barely imagine. Modern systems can detect threats at hundreds of miles, can generate countermeasures automatically, can create electromagnetic illusions so sophisticated that enemy sensors become worse than useless. They become actively misleading. The technology is classified, hidden behind security classifications that will probably persist for decades more. But the fundamental truth remains visible to anyone who knows where to look. In the contest between sensors and countermeasures, between those who seek to see and those who seek to deceive, the advantage goes to whoever can lie most convincingly. The fan-song radar was designed to see truth. Crenshaw's jammer was designed to tell lies that looked like truth. And in that contest, the lies won. That victory echoes through every electronic warfare system deployed since 1972. Every jamming pod, every radar warning receiver, every deception system traces its conceptual lineage back to a maintenance hangar in Thailand, to an engineer who understood that sometimes the best way to win is not to be stronger, but to be smarter, not to block your enemy's perception, but to corrupt it. The war ended 50 years ago. The participants are gone or elderly. The equipment has long since been retired, replaced by systems that would seem miraculous to the engineers of that era. But the lesson persists, encoded in doctrine and training and the institutional memory of military forces around the world. When sensors and countermeasures compete, the countermeasures usually win. When power and deception contest, deception often prevails. When institutional procedure and individual innovation collide, sometimes, just sometimes, innovation triumphs despite the rules rather than because of them. That's not a lesson military institutions want to acknowledge. It suggests that rules can be wrong, that procedures can be inadequate, that sometimes breaking regulations is the right thing to do. It's a dangerous lesson, one that could undermine the discipline and standardization that large organizations require to function. But it's also a true lesson, and truth, in the end, matters more than comfort.